Imagine staring up at the night sky, knowing that hidden within its vast expanse lies a cosmic mystery so baffling it's puzzled scientists for decades. The universe, for all its grandeur, is missing something fundamental: lithium. This simple element, the third lightest in the periodic table, should be everywhere. The Big Bang scattered it across the cosmos in amounts we can calculate, yet when we look, it's not there. Where did it go? Why is there so much less lithium than our models predict? This isn't just a small oversight, it's a gaping hole in our understanding of how the universe works. And here's the thrilling part: this missing lithium might hold the key to unlocking secrets about the birth of stars, the fabric of space-time, and even the very nature of dark matter. For years, astronomers have chased this enigma, piecing together clues like detectives solving the ultimate cosmic cold case. From the depths of ancient stars to the far reaches of interstellar gas clouds, they've uncovered 25 tantalizing hints, each one a breadcrumb leading us closer to the truth. Some of these clues point to bizarre stellar processes that devour lithium like a hidden furnace. Others suggest wilder possibilities, like undiscovered particles or even flaws in our most cherished theories of physics. Every answer seems to raise new questions, and that's what makes this mystery so exhilarating. It's not just about lithium, it's about rewriting what we know of the universe's story. So, if you've ever wondered how science tackles the unknown, or if you love a good cosmic whodunit, you're in the right place. This journey will take us from the fiery cores of the first stars to the cutting-edge telescopes probing the edges of reality. We'll explore how something as small as a lithium atom can shake the foundations of astrophysics, and why solving this puzzle could change everything. The universe has left us a trail of clues. Let's follow them together. The Big Bang didn't just give us a universe, it gave us a recipe. In those first fiery minutes, protons and neutrons fused into the simplest elements like hydrogen, helium, and crucially, lithium. Think of it as a cosmic kitchen where the conditions were so precise, scientists can still calculate exactly how much of each ingredient should have been made. And according to those calculations, there should be about 3 times more lithium in the universe than what we actually see. That's not a rounding error. It's a glaring inconsistency, like baking a cake and finding half the flour mysteriously vanished. This mismatch isn't just a small hiccup in our models, it's a direct challenge to our understanding of the universe's infancy. Big Bang Nucleosynthesis, the process that forged those first elements, is one of the most well-tested pillars of modern cosmology. Everything from the cosmic microwave background to the abundance of hydrogen and helium fits beautifully with predictions. But lithium, it's the outlier, the one piece that refuses to fall into place. If our math is right, and we're pretty sure it is, then where did all that lithium go? One possibility is that something destroyed it after the Big Bang. Imagine lithium as delicate sandcastles on a cosmic shoreline, vulnerable to the tides of stellar winds or the crashing waves of interstellar radiation. Ancient stars, some of the universe's firstborn, might have acted like lithium shredders, their intense heat and pressure breaking the element down into simpler particles. Or perhaps lithium got trapped in places we can't easily see, like the cores of stars or hidden pockets of gas between galaxies. But there's an even wilder option. What if our predictions are wrong, not because the math is flawed, but because there's physics at play we haven't discovered yet? Some theories suggest exotic particles, like certain types of dark matter, could have interacted with lithium in ways we don't yet understand, essentially erasing it from the cosmic ledger. Others propose that the early universe wasn't as uniform as we think. Tiny fluctuations in temperature or density might have skewed lithium production in ways our models can't yet account for. Whatever the answer, this lithium discrepancy is more than just a missing puzzle piece. It's a flashlight shining into the shadows of cosmology, revealing cracks in our theories we didn't even know were there. Solving it could rewrite chapters of the universe's history, from the first seconds after the Big Bang to the life cycles of the oldest stars, and that's just the first clue. Stars might seem eternal, unchanging, but they're actually cosmic alchemists constantly transforming matter in their cores, and lithium, it's one of their first victims. Unlike heavier elements that can withstand stellar furnaces, lithium is fragile. At temperatures found deep inside most stars, it breaks apart almost instantly. This means that as stars age, they burn through their lithium reserves like a candle consuming its wax. But here's the catch: not all stars destroy lithium at the same rate. Young stars, fresh from the cosmic nursery, often have plenty of it. Old stars, on the other hand, show barely a trace. That stark difference is one of our biggest clues in the missing lithium mystery. Take the Sun, for example. Our own star has about 140 times less lithium than the cloud of gas it formed from. Where did it all go? The answer lies in how stars churn their interiors. Many Sun-like stars have conveyor belts of plasma, rising hot material and sinking cooler material, that drag lithium down into their cores where it's obliterated. But some stars, especially those with slower internal circulation, hold onto their lithium longer. By studying these differences, astronomers can piece together a timeline of lithium loss, almost like reading tree rings to understand a forest's history. Then there are the outlier stars that defy expectations. Some ancient stars, nearly as old as the universe itself, still show surprising amounts of lithium, while others of the same age have almost none. Why the discrepancy? One theory points to cosmic collisions. If a star swallows a lithium-rich planet or a cloud of gas, it might temporarily boost its lithium levels before burning it away. Another possibility involves stellar spin. Fast-rotating stars might mix their interiors less efficiently, creating lithium-safe zones where the element can hide from destruction. But the most intriguing twist comes from brown dwarfs, failed stars too small to ignite full fusion. These cosmic misfits act like lithium traps. Because their cores never get hot enough to destroy lithium, they preserve it like time capsules. By measuring lithium in these objects, astronomers get a snapshot of how much was available in their birth clouds, offering another clue to the universe's original lithium budget. Every observation adds another piece to the puzzle, revealing how stars, from the mightiest giants to the humblest dwarfs, shape the cosmic story of this elusive element. So while stars may be the culprits behind lithium's disappearance, they're also the key witnesses. Their varied lithium fingerprints tell us not just about stellar evolution, but about the broader history of our universe. And that's just the beginning, because if stars are destroying lithium, where does that leave the rest of the missing supply? The answer might lie in places even more unexpected. Cosmic rays, those high-energy particles zipping through space at nearly the speed of light, might hold another piece of the lithium puzzle. When these rays smash into heavier atoms like carbon or oxygen, the collisions can shatter them, breaking their nuclei apart in a process called spallation. And here's the kicker: one of the fragments left behind can be lithium. It's like hitting a bowling ball with a sledgehammer. Sometimes the pieces that fly off include tiny lithium nuclei. But if spallation creates lithium, how does it help explain the universe's lithium shortage? The answer lies in the delicate balance between creation and destruction. While spallation can produce lithium, those same cosmic rays can also destroy it. High-energy protons or alpha particles, common components of cosmic rays, can collide with lithium nuclei and tear them apart, turning them back into smaller particles. Think of it as a cosmic game of Jenga. Just as one block gets added, another gets pulled out, and the whole structure stays unstable. Astronomers have spotted this tug-of-war in action. In regions like the Orion molecular cloud, where young stars blast out intense radiation and cosmic rays, lithium levels fluctuate wildly. Some pockets show spikes in lithium abundance, likely from fresh spallation, while nearby areas appear almost barren, as if the element was erased by the same energetic processes. Even more telling, when scientists analyze the isotopic ratios of lithium in these environments, they find clues. Lithium-7, the most common stable isotope, is often scarcer than expected, while lithium-6, which forms more easily in spallation, sometimes appears in higher amounts. This mismatch hints at a brutal cycle: cosmic rays giveth and cosmic rays taketh away. Yet the story gets even stranger when we look beyond our galaxy. In the vast, diffuse gas clouds between galaxies, where cosmic rays roam freely, lithium levels are mysteriously low. If spallation were the dominant process, we'd expect more lithium in these regions, not less. That suggests something else, something bigger, is at work. Could primordial lithium have been wiped out early in the universe's history, before cosmic rays even had a chance to replenish it? Or are we missing a critical piece of physics that governs how lithium behaves in extreme environments? The deeper we dig, the clearer it becomes. Cosmic rays aren't just background noise in the universe. They're active players in the lithium drama, both creating and erasing it in a cycle that's left scientists scrambling to account for every last atom. And if we're ever going to solve the mystery of the missing lithium, we'll need to understand not just where it's hiding, but where it's being destroyed. Galaxies aren't just static islands of stars, they're dynamic, ever-changing ecosystems where elements like lithium are constantly being reshuffled, created, and destroyed. To understand why lithium levels vary across the cosmos, we need to dive into galactic chemical evolution, the grand process by which galaxies transform their chemical makeup over billions of years. Picture a galaxy as a giant recycling plant. Stars are born from interstellar gas, fuse light elements into heavier ones, and eventually die, spewing enriched material back into space. But lithium doesn't always follow the script. In young galaxies where star formation is rampant, lithium gets caught in the crossfire. Massive stars burn through it at breakneck speeds, while supernova and stellar winds blast it out into the interstellar medium. Some of this lithium might cling to dust grains or get trapped in molecular clouds, hidden from our telescopes. Meanwhile, newer generations of stars form from this lithium-depleted gas, starting the cycle all over again. It's like pouring water into a leaky bucket. No matter how much lithium the Big Bang originally made, galaxies keep losing it over time, but not all galaxies behave the same way. Dwarf galaxies, for example, tell a different story. These small, faint systems often have slower star formation rates, meaning they don't burn through lithium as aggressively. Some even show higher lithium abundances than expected, as if they've been hoarding it while their larger cousins threw it away. Then there's the interstellar medium, the vast, diffuse gas between stars. In some regions, lithium appears to cling stubbornly to dust particles, effectively disappearing from our measurements until something disturbs it, like a shock wave from a nearby supernova. The plot thickens when we look at galactic mergers. When two galaxies collide, their gas clouds smash together, triggering bursts of star formation that can either destroy lithium or, under rare conditions, even produce more of it. These chaotic events might explain why some galaxies have bizarre lithium signatures that defy predictions. Add to this the role of cosmic rays, which, as we've seen, can both create and destroy lithium, and you've got a galactic-scale tug-of-war with no clear winner. What's fascinating is how this connects to the broader universe. If galaxies are all losing lithium over time, why isn't the deficit even worse? Could there be hidden reservoirs, places where lithium survives undetected? Or are we underestimating how much gets replenished by processes we don't fully understand? Each galaxy is like a piece of forensic evidence, and by studying their chemical fingerprints, we're one step closer to solving the mystery of the missing lithium. Among the oldest stars in the universe, there's a whisper of the cosmos' earliest secrets, and their lithium levels are telling a story that doesn't quite add up. These ancient celestial relics, some nearly 13 billion years old, were born from gas clouds forged in the aftermath of the Big Bang. They're like cosmic fossils, preserving the chemical makeup of the infant universe. And here's the puzzle: when we measure their lithium, it's far scarcer than our models predict. If the Big Bang sprinkled lithium evenly across the cosmos, why do these primordial stars show such a glaring shortfall? Take the Methuselah star, for instance. This ancient sun, one of the oldest ever discovered, has lithium levels a fraction of what our calculations say it should. It's not alone. Dozens of similarly aged stars show the same discrepancy. The strangest part, these stars are so pristine, so untouched by later generations of cosmic recycling, that their lithium deficit can't be blamed on stellar processes alone. Their atmospheres are time capsules, locking in the chemistry of the universe's first few 100 million years. So if lithium was there at the beginning, how did it vanish so quickly? One leading theory points to stellar atmospheres themselves. These ancient stars are cooler and more convective than younger ones, meaning their outer layers constantly churn, dragging material from the surface down into searing hot interiors where lithium is destroyed. Imagine a pot of boiling water. If you drop in a handful of ice cubes, they'll melt almost instantly. Similarly, any lithium in these stars' outer layers gets pulled inward and obliterated before we can observe it. But even this explanation has cracks. Some stars with similar ages and temperatures show slightly higher lithium levels, as if they've managed to cling to a few precious atoms against the odds. Then there's the possibility of pre-stellar depletion. Before these ancient stars even formed, could something have already scrubbed lithium from their birth clouds? Cosmic rays, as we've seen, can break lithium apart, but in the early universe, radiation from the first massive stars and supernova might have been intense enough to wipe out lithium on a galactic scale. Or perhaps exotic physics, like interactions with dark matter particles, played a role. Some theories suggest certain types of dark matter could have absorbed or transformed lithium in ways we don't yet understand, leaving these stars with less than their fair share. What makes these ancient stars so crucial to the mystery is their simplicity. Unlike younger stars, which are polluted by generations of supernova debris and planetary collisions, these relics offer a clean window into the past. Their lithium deficit isn't just a curiosity, it's a direct challenge to our understanding of the universe's chemical infancy. If we can figure out why they're missing lithium, we might finally solve a puzzle that's lingered since the first moments of time. And that answer could rewrite everything we thought we knew about the dawn of the cosmos. Brown dwarfs are the universe's failed stars, too massive to be planets, yet not quite heavy enough to ignite full fusion in their cores. These cosmic in-betweeners might seem irrelevant to the lithium mystery at first glance, but they're actually some of our best witnesses. Because they never reach the scorching temperatures needed to burn lithium, these objects act like celestial storage lockers, preserving the element exactly as it was when they formed. Study a brown dwarf, and you're peering into a time capsule of the universe's original lithium supply. But here's where things get interesting. Not all brown dwarfs play by the rules. While most should hold onto their lithium indefinitely, astronomers have spotted a handful with bafflingly low levels, as if something's been nibbling away at their reserves. Take the brown dwarf known as PSOJ 318.5-22. This dim, cool object sits right on the boundary between star and planet, and yet it's missing nearly all its expected lithium. The kicker, its temperature isn't high enough to destroy the element naturally. So where did the lithium go? One theory points to a phenomenon called convective mixing. Brown dwarfs, especially the warmer ones, can churn their interiors like a slow-motion lava lamp. If lithium gets dragged deep enough, even the relatively mild heat at the bottom of these churning layers might be enough to break it apart. Think of it like dropping an ice cube into lukewarm water. It won't vanish instantly, but given enough time, it'll still dissolve. That could explain why some older brown dwarfs show lithium depletion while younger ones don't. Time in this case might be the silent thief. Then there's the wild card, accretion. Some brown dwarfs might have devoured lithium-rich planets or asteroids early in their lives, temporarily boosting their levels before internal processes wipe the slate clean. Imagine a cosmic game of Pac-Man where the brown dwarf gobbles up lithium-rich material, only for its own machinery to erase the evidence later. But the real curveball comes from recent observations of brown dwarfs with extra lithium. A few of these oddballs, like the one catalogued as 2 mass J0355 plus 1133, show lithium abundances that defy expectations. Their atmospheres glow with spectral lines indicating far more lithium than standard models predict. Could these objects have formed in lithium-rich pockets of interstellar gas? Or is there some exotic process like interactions with dark matter or primordial magnetic fields that's artificially inflating their lithium reserves? Every brown dwarf we study adds another layer to the mystery. Some guard their lithium like treasure, while others seem to have let it slip through their fingers. And in that inconsistency lies a clue, a hint that the universe's missing lithium isn't just vanishing in one way, but many. Whether it's being destroyed, hidden, or transformed, one thing's clear: brown dwarfs are far more than failed stars. They're the universe's record keepers, holding secrets to a cosmic crime we're only beginning to unravel. Supernova are the universe's ultimate demolitions experts, violent, chaotic, and capable of reshaping entire galaxies. When a massive star reaches the end of its life and explodes, it doesn't just vanish in a blaze of glory. It scatters its guts across space, hurling newly forged elements into the cosmos. But lithium, that fragile third element, faces a perilous journey in this stellar apocalypse. These explosions should, in theory, both create and obliterate lithium, leaving behind a cosmic fingerprint that could help solve our mystery. Take Cassiopeia A, one of the most studied supernova remnants. When astronomers analyze its debris, they find a cocktail of heavy elements like iron and silicon, but lithium is conspicuously scarce. That's odd because supernova should produce some lithium through a process called neutrino spallation. Here's how it works. During the explosion, a flood of neutrinos, those ghostly, nearly massless particles, slam into heavier nuclei, chipping off fragments that can include lithium. It's like knocking crumbs off a loaf of bread. The crumbs might be tiny, but they add up. Yet in remnants like Cassiopeia A, those crumbs are missing. The problem gets stranger when we compare different types of supernova. Core collapse supernova, the dramatic deaths of massive stars, should generate lithium through neutrino interactions, but the amounts we detect are far lower than predicted. Meanwhile, Type Ia supernova, which occur when white dwarfs explode, don't produce lithium at all. In fact, their extreme heat and pressure would vaporize any pre-existing lithium in the vicinity. Imagine tossing a snowflake into a blast furnace. That's essentially what happens to lithium near these events. But here's the twist: some supernova might actually preserve lithium, at least temporarily. In the outer layers of a dying star, where temperatures are cooler, lithium can survive long enough to be ejected before the explosion's shockwave catches up. It's like escaping a collapsing building just seconds before the roof caves in. Astronomers have spotted hints of this in a handful of supernova remnants, where lithium lingers in the cooler, less processed debris at the edges. The challenge: these surviving atoms are incredibly hard to detect, drowned out by the cacophony of heavier elements. The real shocker comes when we look beyond individual remnants. If supernova were major lithium producers over cosmic time, we'd expect to see more of it in younger stars born from their ashes. Instead, the opposite seems true. Regions with recent supernova activity often show lower lithium levels. That suggests these explosions aren't just failing to contribute lithium, they might be actively destroying it. Perhaps the intense radiation and shock waves from supernova break apart lithium atoms in nearby gas clouds, erasing them before new stars can form. This leaves us with a paradox. Supernovae are among the most powerful engines of chemical change in the universe, yet their role in the lithium saga is murky at best. They might giveth, but they definitely taketh away, and until we unravel precisely how, this clue remains as explosive as the phenomena behind it. Meteorites are more than just space rocks. They're time capsules preserving the chemistry of the solar system as it was over 4.5 billion years ago. Unlike Earth, where geological activity and weathering have erased much of our planet's original makeup, these ancient fragments remain almost untouched. And when it comes to lithium, they hold a record of cosmic history that's both revealing and deeply puzzling. Take the Allende meteorite, for example. This carbonaceous chondrite, which fell in Mexico in 1969, contains minerals that formed before the planets themselves. When scientists measured its lithium content, they found something unexpected. The levels were significantly lower than what Big Bang Nucleosynthesis predicts. That's a problem because if meteorites which formed from the same primordial cloud as the Sun and planets are lithium deficient, it suggests the shortage isn't just a modern phenomenon. The lithium was already missing when the solar system was born, but here's the twist: not all meteorites tell the same story. While most chondrites show lithium levels below expectations, some rare types, like enstatite chondrites, have curiously higher amounts. These variations hint at a complex history. Perhaps lithium wasn't evenly distributed in the solar nebula, or maybe local processes, like heating from nearby stars or cosmic rays, altered its abundance in certain regions before meteorites formed. It's like finding pages torn from a cosmic ledger, with some entries mysteriously erased while others remain intact. Even more intriguing are the iron meteorites. These metallic remnants of ancient planetary cores contain almost no lithium, which makes sense. Heavy elements like iron sank to the centers of protoplanets, leaving lighter elements like lithium behind in their crusts. But when we compare them to stony meteorites, the discrepancy raises questions. If lithium was so scarce in the early solar system, why do some rocks still hold traces while others don't? The answer might lie in temperature. Meteorites that experienced intense heat, like those that were part of larger bodies that melted and differentiated, lost their lithium to vaporization. Cooler, less processed samples held onto theirs, like a cosmic deep freezer preserving delicate ingredients. Then there's the interstellar angle. Some meteorites contain grains of stardust, actual particles from other stars older than the Sun itself. These microscopic time capsules sometimes show lithium levels that defy expectations, as if their parent stars had unusual chemical histories. One theory suggests that certain red giants or asymptotic giant branch stars might produce lithium in their late stages, sprinkling it into the galaxy like cosmic salt. If so, these grains could be evidence of lithium factories we've overlooked, places where the element is made rather than destroyed. The real shocker comes when we compare meteorite data to modern measurements. The lithium deficit in these ancient rocks lines up eerily well with what we see in stars and interstellar gas today. That suggests the missing lithium problem isn't something that developed over time. It was baked into the universe from the start. The Big Bang made less lithium than we thought, or something wiped it out almost immediately. Either way, meteorites aren't just clues. They're silent witnesses to a cosmic theft that happened before the Earth even existed. And if we want to solve the mystery, we'll need to dig deeper into the chemistry of the cosmos and the secrets these ancient stones still hold. Among the most baffling clues in the lithium mystery is a phenomenon astronomers call the lithium plateau, a strange consistency in lithium levels among some of the oldest, most metal-poor stars in the universe. These ancient stars, born when the cosmos was just a fraction of its current age, should vary wildly in their lithium content based on their size, temperature, and environment. Yet when scientists measure them time and again, they find nearly identical amounts of lithium in their atmospheres. It's as if some cosmic rulebook forced them to adhere to the same strict quota, defying all expectations. Take the star HD 140283, for instance. This elderly giant, nearly as old as the universe itself, has barely a trace of heavier elements like iron or carbon, yet its lithium levels match those of other similarly ancient stars with surprising precision. Even more puzzling, stars with slightly more metals, 10 or 20 times as much, still cling to that same lithium plateau, as if some unseen mechanism were enforcing a universal baseline. This isn't just a curiosity, it's a direct challenge to our understanding of how elements spread through the early cosmos. One leading theory suggests this plateau might be a fossil of sorts, a relic of the Big Bang itself. If lithium was uniformly scattered across the universe in its infancy, and if these stars formed before processes like convection or cosmic rays could alter their lithium content, then their consistent levels might reflect the universe's original lithium supply. Picture a pristine lake frozen in time, its waters untouched by evaporation or pollution. These stars could be the cosmic equivalent, preserving lithium's primordial abundance like a snapshot of the past. But there's a glaring hole in that idea. The plateau's lithium levels are still far lower than Big Bang predictions. If these stars are truly untouched time capsules, why don't they match our calculations? Some researchers argue that even these ancient stars aren't perfect preservers. Their outer layers might still churn over billions of years, slowly dragging lithium down to their cores where it's destroyed. Others propose a more radical solution. Perhaps the plateau isn't primordial at all. Instead, it could be the work of an unknown cosmic process, something that reset lithium levels in these stars long after their birth. Imagine a stellar-scale blender, some early universe phenomenon that mixed gas clouds so thoroughly it homogenized their lithium content before stars formed. Or consider the possibility of lithium-depleting dark matter interactions, exotic particles that selectively destroyed the element in certain regions, leaving behind a uniform deficit. The plateau's very existence hints at forces we haven't yet uncovered, lurking in the gaps of our models. What makes this clue so crucial is its universality. From the Milky Way to distant dwarf galaxies, metal-poor stars keep echoing the same lithium value, like a cosmic chorus singing in perfect harmony. That consistency is either a smoking gun, pointing to a fundamental flaw in our understanding of the Big Bang, or evidence of a hidden hand, some mechanism that quietly regulated lithium levels before most stars were even born. Either way, the plateau isn't just a curiosity. It's a breadcrumb leading us deeper into the lithium mystery, toward answers that might reshape our view of the cosmos itself. Deep inside stars like our Sun, a slow but relentless process is quietly stealing lithium away, not by destroying it outright, but by hiding it beyond our sight. This phenomenon, known as microscopic diffusion, acts like a cosmic conveyor belt, dragging lithium atoms from a star's outer layers down toward its searing core. Picture a handful of glitter tossed into a swimming pool. Initially, it sparkles at the surface, but over time, the flakes drift downward, disappearing into the depths. That's exactly what happens to lithium in solar-type stars, and it's one of the most insidious culprits behind the missing lithium mystery. Take the Sun as a prime example. Spectroscopic measurements reveal its surface lithium abundance is a staggering 100 times lower than the protostellar cloud it formed from. Yet we know the Sun hasn't burned through all that lithium. Its core temperature isn't high enough to obliterate the element completely. So where did it go? The answer lies in the star's internal dynamics. Unlike massive stars which churn their interiors violently, Sun-like stars have a quieter but equally effective mixing mechanism. Beneath the turbulent outer convection zone lies a stable radiative layer where photons, not gas motion, transport energy. Here, lithium atoms, slightly heavier than the surrounding hydrogen, gradually sink due to gravity's pull. It's a staggeringly slow process, like sand trickling through an hourglass, but over billions of years, it's enough to strip the star's observable layers clean. This explains why lithium depletion varies so dramatically among stars of similar age and mass. A star's rotation plays a starring role. Faster spinning stars resist this sinking effect because their centrifugal force and magnetic activity create turbulence, effectively stirring lithium back toward the surface like a spoon in coffee. Meanwhile, slower rotators like our middle-aged sun allow lithium to sink unimpeded. Astronomers see this divide clearly in open star clusters, where siblings born from the same gas cloud show wildly different lithium levels. In the Hyades cluster, for instance, stars with identical compositions display lithium discrepancies of up to tenfold, all thanks to subtle differences in spin and internal structure. But diffusion isn't the only thief at work. Stars also experience macroscopic motions, large-scale currents that dredge lithium from the surface and plunge it into fusion-ready zones. In some cases, these currents might even explain bizarre outliers, like stars that temporarily regrow lithium in their spectra. Imagine a sunspot-driven upheaval that temporarily unearths long-buried lithium reserves, giving astronomers a fleeting glimpse of what's been hidden below. These chaotic events muddy the waters, making it even harder to pin down exactly how much lithium a star truly started with. The implications stretch far beyond our solar neighborhood. If diffusion and mixing routinely cloak lithium in sun-like stars across the galaxy, we're left with a universe where the element's true abundance is systematically undercounted. That means the cosmic lithium deficit might not be as severe as we think. It's just been hiding in plain sight, tucked away in stellar interiors like treasure locked in a vault. But here's the catch: even if we account for this sinking, the numbers still don't add up. There's more missing lithium than stars alone can explain, which means the mystery runs deeper than diffusion alone. And that's what makes this clue so tantalizing. It's not the full answer, but it's a critical piece of the puzzle, revealing how the universe plays a cosmic shell game with one of its lightest elements. Stars that spin faster don't just show off, they destroy lithium with terrifying efficiency. Imagine stirring a cup of hot tea while sugar dissolves at the bottom. The faster you swirl the spoon, the quicker the sugar vanishes into the liquid. That's essentially what happens in rapidly rotating stars, where their dizzying spins churn their interiors like cosmic blenders, dragging lithium down into their scorching cores where it gets obliterated. This isn't just theoretical. Observations of star clusters reveal a stark pattern. The quicker a star rotates, the less lithium it tends to hold on to. Take the Pleiades, for example. This young star cluster, glowing bright in our night sky, is a laboratory for studying stellar spin. Astronomers have measured rotation rates and lithium levels in hundreds of its stars, uncovering a clear trend. The fastest spinning members show lithium deficits up to 10 times greater than their slower counterparts. Why? Because rapid rotation amplifies turbulence in a star's outer layers, creating currents that dredge lithium downward into hotter regions where it can't survive. It's a brutal feedback loop. More spin means more mixing, which means less visible lithium. But there's a twist. Not all fast rotators behave the same way. Some stars, particularly those with strong magnetic fields, buck the trend. Their magnetic activity can actually create pockets of stability, shielding lithium from destruction even as the star whips around at high speed. Picture a tornado tearing through a town, but certain houses, those built with reinforced foundations, remain standing. That's what magnetic fields do for lithium in these chaotic stellar environments. The stakes get even higher when we look at binary star systems. twin stars born from the same gas cloud often have wildly different rotation rates and lithium levels, despite sharing the same age and composition. In some cases, one star spins lazily, preserving its lithium like a careful collector, while its sibling whirls so fast it shreds its lithium reserves within a few 100 million years. These cosmic twins shouldn't be so different, yet they are, hinting at complex interactions between rotation, magnetic fields, and even unseen planets that might have altered their spin histories. This clue isn't just about stars, it's about time. Rotation rates change as stars age, slowing down due to magnetic braking. That means a star's current lithium levels encode a history of its past behavior. A middle-aged star with unusually low lithium might have been a rapid rotator in its youth, its spin long since slowed but its lithium deficit remaining like a scar. By decoding these patterns, astronomers can reconstruct the life cycles of stars across billions of years, tracing how rotation sculpts the universe's elemental inventory. Yet even this explanation leaves gaps. Some stars rotate slowly but still show extreme lithium depletion, while others spin furiously yet cling to surprising amounts. Clearly, rotation isn't the whole story, but it's a critical piece of the puzzle, proving that a star's dance through space doesn't just shape its own fate. It leaves an indelible mark on the cosmos' chemical legacy, one atom at a time. If stars and brown dwarfs can't account for all the missing lithium, maybe we've been looking in the wrong places entirely. Enter exoplanets, those distant worlds orbiting other stars which could be silently hoarding lithium in their atmospheres like cosmic vaults. The idea isn't as far-fetched as it sounds. Just as Jupiter's thick clouds trap ammonia and methane, gas giants around other stars might be cloaking vast reserves of lithium, hiding it from our telescopes. The challenge, detecting it, demands precision bordering on the impossible. Take hot Jupiters, for example. These blistering gas giants orbit perilously close to their stars, their atmospheres stretched into bloated, puffy layers by intense heat. Under these extreme conditions, lithium atoms could rise high enough to leave faint fingerprints in the light, passing through them spectral lines that astronomers might spot with next-generation instruments. But even then, the signals are whisper-thin. Detecting lithium in an exoplanet's atmosphere isn't like finding a billboard. It's more like spotting a single grain of sand on a windy beach. Recent surveys have added tantalizing hints. The exoplanet WASP 127b, a hot Jupiter with a surprisingly clear atmosphere, showed tentative signs of alkali metals including lithium during transit observations. While not yet confirmed, the possibility sent ripples through the astronomy community. If validated, it would prove that planets can act as lithium reservoirs, locking the element away in their gaseous envelopes for billions of years. Even more intriguing are super-puff planets, like those in the Kepler-5.1 system, with atmospheres so extended they resemble cotton candy. These worlds might harbor lithium in their upper layers where cooler temperatures prevent its destruction. But here's the catch. While gas giants could stash lithium, rocky exoplanets might be actively destroying it. Planets like Earth have geological processes, volcanism, plate tectonics, that recycle surface material into their mantles, dragging lithium deep underground where it's inaccessible. That means the lithium budget of the universe could depend heavily on what type of planets dominate a given system. A galaxy teeming with gas giants might preserve lithium, one filled with rocky worlds could erase it. The real game changer could come from direct imaging of young exoplanets. In systems still forming, protoplanetary disks might contain lithium-rich gas that gets baked into newborn planets before stars have a chance to burn it away. Instruments like the James Webb Space Telescope are just beginning to probe these infant worlds, searching for chemical signatures that could rewrite our understanding of planetary and cosmic evolution. So while exoplanets might not solve the lithium mystery alone, they're a critical piece of the puzzle. Whether they're hiding it, destroying it, or simply redistributing it, their role in the universe's elemental cycle is far more dynamic than we ever imagined. And as our technology improves, we might finally catch these distant worlds in the act, revealing their secrets one atom at a time. Stellar magnetic fields are like invisible hands, sculpting the fate of lithium in ways we're only beginning to understand. While rotation churns a star's interior, magnetism adds another layer of complexity, twisting, compressing, and accelerating the destruction of this fragile element. Imagine a star's magnetic field as a network of superhighways where charged particles, including lithium ions, get funneled toward regions of intense heat, speeding up their demise. This isn't just theoretical. Observations of magnetically active stars reveal lithium deficits far more severe than their common counterparts, as if magnetism is turning up the dial on depletion. Take the star Tau Boötis, for example. This yellow dwarf isn't just magnetically active, it's a powerhouse with a field thousands of times stronger than the Sun's. When astronomers measured its lithium levels, they found barely a trace despite its relatively young age. The culprit, its magnetic field, appears to be driving turbulent, mixing deep into its radiative zone, dredging lithium from the surface and plunging it into the fusion furnace below. It's like a cosmic conveyor belt on overdrive, working overtime to erase the element from existence. But magnetism doesn't always play the villain. In some stars, particularly those with complex tangled field lines, the opposite happens. Magnetic activity can create pockets of stability zones where lithium is shielded from destruction. Picture a maze of magnetic barriers, corralling lithium atoms into cooler, quieter regions where they survive against the odds. Stars like Kappa Ceti, a young solar analog with a robust magnetic field, show precisely this paradox. Despite their high activity, they retain surprising amounts of lithium, as if their magnetism built a fortress around the element rather than a death trap. The most compelling evidence comes from star clusters, where siblings with similar ages and compositions display wild variations in lithium based on magnetic activity. In the Hyades cluster, for instance, stars with stronger magnetic fields tend to have less lithium, but only up to a point. Beyond a certain threshold, the trend reverses, suggesting magnetism's role isn't linear but dynamic, flipping between destruction and preservation depending on the star's unique conditions. This duality hints at something deeper. Magnetic fields might not just accelerate lithium depletion. They could also redistribute it, hiding it in stellar atmospheres or even ejecting it into space via stellar winds. Some studies suggest that flaring M-dwarfs, notorious for their violent magnetic outbursts, might actually expel lithium from their surfaces during eruptions, spraying it into interstellar space like a cosmic sprinkler. The implications stretch beyond individual stars. If magnetic fields are this influential, they could explain why lithium levels vary so dramatically across galaxies, with some regions appearing nearly barren while others cling to unexpected reserves. It's a reminder that the universe rarely follows simple rules, and that solving the lithium mystery will require unraveling the tangled dance between magnetism, rotation, and the hidden life cycles of stars. Between the stars, far from the blazing heat of stellar cores, floats a diffuse sea of gas and dust, the interstellar medium. This vast, often overlooked region might hold crucial clues to the lithium mystery. After all, if stars destroy lithium and planets hide it, could the spaces between them be hoarding the missing supply? The answer isn't simple. While the interstellar medium is mostly hydrogen and helium, spectroscopic surveys have revealed whispers of lithium drifting through these cosmic voids. Yet the amounts detected are bafflingly low, raising more questions than answers. Take the work of radio telescopes like the Green Bank telescope, which has scanned the interstellar medium for lithium's faint spectral signature. In regions like the Taurus molecular cloud, a stellar nursery rich in gas and dust lithium appears in trace amounts, clinging to dust grains or floating as isolated atoms. But here's the catch: even in these dense pockets, lithium levels are far below what cosmic models predict. It's as if the interstellar medium isn't just a bystander in this mystery. It's an active participant, somehow losing lithium faster than it can accumulate. One leading theory points to cosmic rays, those high-energy particles we've met before, as interstellar lithium's unseen executioner. When these rays slam into interstellar gas, they can break apart lithium nuclei, effectively erasing the element from the inventory. But that's not the only threat. Ultraviolet radiation from nearby stars can ionize lithium atoms, stripping them of electrons and making them nearly invisible to our telescopes. Imagine trying to count fireflies in a stadium flooded with spotlights. That's the challenge astronomers face when hunting for lithium in the glare of stellar radiation. The plot thickens when we look at different environments. In the diffuse, low-density regions between stars, lithium is scarce, but in denser molecular clouds where new stars are born, it's practically absent. This gradient suggests that lithium isn't just hiding, it's being actively destroyed or transformed as gas condenses into star-forming regions. Some models propose that lithium binds to dust grains in these clouds, forming molecules like lithium hydride that our current instruments struggle to detect. Others argue that shocks from supernova or stellar winds blast lithium out of these regions entirely, scattering it into intergalactic space where it's nearly impossible to track. The most tantalizing clue comes from isotopic ratios. In the interstellar medium, lithium-6, the rarer isotope sometimes appears overabundant relative to lithium-7. Since cosmic rays produce more lithium-6 through spallation, this imbalance hints that the interstellar medium isn't just losing lithium, it's reprocessing it. Picture a cosmic recycling plant where lithium gets broken down and rebuilt, with some versions favored over others. All this paints a paradoxical picture. The interstellar medium should be a reservoir for the universe's lithium, a place where it accumulates over billions of years. Instead, it looks more like a sieve, with the element slipping through the cracks faster than we can account for. Whether it's being destroyed, hidden, or ejected, one thing's clear: the spaces between stars aren't the sanctuary we hoped they'd be. They're another crime seen in the great cosmic mystery of the missing lithium. Neutrinos are the ghosts of the particle world, ethereal, nearly massless, and capable of passing through entire planets without leaving a trace. Yet these elusive particles might hold the key to one of lithium's greatest disappearing acts. The theory goes like this: in the chaotic aftermath of the Big Bang, or deep within stars, neutrinos could have smashed into lithium nuclei with enough force to shatter them, breaking the fragile atoms into smaller pieces. It's a radical idea, suggesting that something barely detectable might be responsible for erasing an entire element from the cosmic ledger. The evidence comes from supernova, where neutrino spallation is already known to occur. When a massive star explodes, it releases a flood of neutrinos, so many that even with their feeble interactions, they can chip away at heavier elements, producing lighter ones like lithium in the process. But here's the twist: those same neutrinos might also destroy lithium if they hit it just right. Imagine a sledgehammer swinging at a house of cards. Sometimes it knocks loose a single card, but other times it obliterates the whole structure. That's the neutrino's dilemma. It can both create and annihilate lithium, depending on the energy and angle of collision. Critics of this hypothesis point to the numbers. Neutrinos interact so rarely with matter that even in the dense cores of stars or the searing plasma of the early universe, their impact on lithium should be minimal. Calculations suggest they'd need impossibly high energies far beyond what most astrophysical environments provide to break lithium apart efficiently. Yet there's a loophole. What if we're underestimating neutrino flavors or their interactions with hypothetical particles? Some theories propose sterile neutrinos, a heavier, even more elusive cousin, could be the culprits, lurking in the shadows of particle physics and packing enough punch to disrupt lithium on a cosmic scale. The strongest support comes from anomalies in stellar lithium patterns. Certain stars, like those in globular clusters, show lithium depletions that can't be explained by convection or rotation alone. Their deficits align eerily well with models where neutrinos selectively target lithium, peeling it away layer by layer over billions of years. Even more compelling are observations of lithium-6 in meteorites, which is oddly scarce compared to lithium-7. Neutrino interactions could preferentially destroy the lighter isotope, leaving behind a skewed ratio that matches what we see, but the theory isn't bulletproof. If neutrinos were scrubbing lithium from the universe, why don't we see more dramatic variations in places with intense neutrino activity, like near supernova remnants? And why do some stars with similar neutrino exposure retain lithium while their neighbors lose it? The inconsistencies suggest that while neutrinos might play a role, they're not the sole villain in this cosmic mystery. What makes this clue so tantalizing is its duality. Neutrinos are both destroyers and creators, capable of shaping the universe's elemental balance in ways we're only beginning to grasp. Whether they are guilty of stealing lithium or just bystanders in a more complex crime, their story forces us to rethink the invisible forces that govern the cosmos. And that's the heart of the lithium mystery. It's not just about a missing element. It's about uncovering the hidden rules of a universe far stranger than we ever imagined. Dwarf galaxies might be small, but when it comes to the lithium mystery, they punch far above their weight. These cosmic underdogs, some no larger than 1,000th the mass of the Milky Way, hold clues that their giant cousins can't provide. Unlike sprawling spirals where stars churn and recycle elements in a relentless cycle, dwarf galaxies are simpler, quieter, and in many ways pristine. Their slower pace of stellar evolution means they preserve chemical relics from the early universe like cosmic time capsules, and their lithium levels tell a story that's completely at odds with what we see elsewhere. Take the Sculptor dwarf galaxy, for example. This faint, ancient system orbits the Milky Way like a ghostly shadow, its stars nearly as old as the universe itself. When astronomers measured its lithium content, they found something startling. While some stars showed expected deficits, others had more lithium than predicted, almost as if the galaxy had been sprinkled with extra helpings of the element long after the Big Bang. That's the opposite of what we see in larger galaxies, where lithium is systematically scarce. Why the discrepancy? One theory points to dwarf galaxies' lack of cosmic pollution. Unlike massive galaxies, which are constantly polluted by supernova and stellar winds, these tiny systems evolve in relative isolation, allowing pockets of primordial gas to survive with their original chemistry intact. Then there's the ultra-faint dwarfs like Segway 1. These dim, star-starved galaxies are so metal-poor they're practically fossils of the early universe. Their lithium levels are all over the map. Some stars show near zero amounts, while others cling to traces that align perfectly with Big Bang predictions. This wild variation suggests something critical. The missing lithium problem isn't uniform across the cosmos. Instead, it's tangled up in local conditions, things like galactic environment, star formation history, or even something as exotic as dark matter interactions. The real shocker comes when we compare dwarf galaxies to their larger counterparts. Massive galaxies, with their frenetic star formation and violent supernova, seem to erase lithium efficiently. But dwarfs, they're inconsistent. Some appear to lose lithium slowly, while others might even produce it through rare processes like cosmic ray spallation or exotic low-mass star nucleosynthesis. This inconsistency is a goldmine for astronomers. It hints that the lithium deficit isn't a single problem with a single solution, but a web of interconnected mysteries, each galaxy a unique thread in the tapestry. What makes dwarfs so special is their simplicity. Without the chaotic churn of larger galaxies, they offer a clearer window into how lithium behaves or misbehaves on cosmic scales. If we can unravel why some of these tiny galaxies hold onto lithium while others don't, we might finally crack the case wide open. After all, in the hunt for missing lithium, sometimes the smallest clues lead to the biggest breakthroughs. Globular clusters are the universe's ancient beehives, dense, spherical swarms of stars bound together by gravity, some nearly as old as the cosmos itself. These celestial time capsules should, in theory, be perfect laboratories for studying primordial lithium. They're stars formed from the same pristine gas cloud under the same conditions, meaning their chemistry should be uniform. Yet when astronomers measured lithium in these clusters, they got a shock. Instead of matching predictions, the numbers were all over the place, as if some unseen hand had reached in and fiddled with the recipe. Take Messier 4, one of the closest globular clusters to Earth. Spectroscopic studies of its stars revealed lithium levels that varied wildly. Some had almost none, while others showed amounts close to what the Big Bang should have produced. This isn't just a minor discrepancy, it's a full-blown rebellion against our understanding of how elements like lithium behave in these environments. If stars in a cluster are born from the same gas, why don't their lithium levels match? One explanation points to the clusters themselves. Globular clusters are extreme places, crammed with stars in such tight quarters that gravitational interactions are constant and violent. Over billions of years, stars might collide, merge, or strip material from one another, scrambling their original chemistry like a cosmic blender. Imagine pouring a glass of water into a swimming pool. Some droplets stay concentrated while others disperse unevenly. That could explain why lithium in these clusters appears patchy, with some stars holding onto their original supply while others lose it entirely. But there's another twist. Certain stars in globular clusters, particularly red giants, show lithium levels that actually increase as they age, defying all expectations. Normally, stars destroy lithium as they evolve, but in these cases it's almost as if they're manufacturing it. One theory suggests these giants might be dredging up lithium from deep within their cores, where it's been hiding since their formation. Another proposes that cosmic rays slamming into the cluster's dense gas pockets could be creating fresh lithium through spallation, giving certain stars an unexpected second wind. The real enigma comes from comparing globular clusters to other stellar populations. Open clusters, which are younger and less dense, don't show the same lithium chaos. Their stars tend to follow predictable depletion patterns, as if playing by the rules. This stark difference hints that something unique is happening in globular clusters, something tied to their age, density, or even their dark matter content. Some researchers speculate that if dark matter interacts with ordinary matter in these crowded environments, it could selectively destroy lithium, leaving behind the uneven distribution we see today. What makes this clue so tantalizing is its refusal to fit neatly into any single explanation. Globular clusters aren't just challenging our understanding of lithium, they're forcing us to rethink how stars evolve in extreme environments. Whether it's collisions, cosmic rays, or something even more exotic, these ancient stellar cities hold secrets that could rewrite the story of the missing lithium once and for all. And until we crack their code, the mystery only deepens. Dark matter makes up 85% of the universe's mass, yet we can't see it, touch it, or even detect it directly. But what if this invisible cosmic puppeteer is pulling strings we never noticed, like stealthily erasing lithium from existence? It's a radical idea, but some physicists argue dark matter might hold the key to the missing lithium problem. Picture this: in the early universe, dark matter particles could have collided with lithium nuclei, breaking them apart like a wrecking ball hitting a house of cards. These interactions would leave no visible trace, just a puzzling absence where lithium should be. One of the most intriguing theories comes from so-called asymmetric dark matter. Unlike traditional models where dark matter particles are their own antiparticles, This version suggests they come in two flavors: particles and antiparticles, that annihilate each other on contact. If these dark matter particles interacted weakly with lithium, they could have selectively destroyed it in the universe's infancy. Imagine a cosmic game of Pac-Man, where dark matter gobbles up lithium atoms without touching hydrogen or helium. This would explain why lithium is the odd element out, disappearing while other light elements remained abundant. Then there's the possibility of dark photons, hypothetical force carriers that could mediate interactions between dark matter and ordinary particles. If dark photons existed, they might have catalyzed reactions that converted lithium into other forms of matter, effectively scrubbing it from the cosmic record. Some models even suggest these processes could have varied across different regions of the early universe, creating the patchy lithium distribution we see today. But the wildest theory involves primordial black holes. These hypothetical objects formed in the first seconds after the Big Bang could consist of dark matter. If they passed through clouds of primordial gas, their gravity might have compressed and heated the material, triggering nuclear reactions that destroyed lithium. Think of it like a bowling ball rolling through fog. Wherever it goes, the mist vanishes. Critics point out the lack of direct evidence. If dark matter were zapping lithium, we'd expect to see anomalies in other light elements, yet hydrogen and helium remain perfectly in line with predictions. Plus, most dark matter models assume it interacts far too weakly with ordinary matter to cause such precise destruction. But here's the kicker: some of the most lithium-depleted stars also orbit in regions with high dark matter density, like the Milky Way's halo. Coincidence, maybe, or maybe it's a clue we're just starting to decipher. The beauty of this idea is its reach. If dark matter is responsible, solving the lithium mystery could give us our first real window into its nature, turning a cosmic accounting error into the key that unlocks the universe's biggest secret. Until then, it remains one of the boldest, most tantalizing possibilities in physics, that the answer to our lithium problem has been hiding in the dark all along. At the violent hearts of galaxies, supermassive black holes churn the cosmos into chaos, and their fury might hold another piece of the lithium puzzle. Active galactic nuclei, those brilliant beacons powered by black holes devouring entire stars, aren't just cosmic spectacles. They're element-shredding factories where temperatures soar to millions of degrees and magnetic fields twist space itself. In this maelstrom, lithium doesn't stand a chance. Take quasars, for example. These ultra-bright AGNs outshine entire galaxies, their light traveling billions of years to reach us. When astronomers analyze their spectra, lithium appears conspicuously absent, especially compared to the surrounding interstellar medium. Why? The answer lies in the accretion disks, those swirling vortexes of gas spiraling into the black hole. At these extreme temperatures, lithium nuclei get torn apart faster than they can form, like paper tossed into a furnace. Even worse, the relativistic jets blasting outward at near light speed can carry lithium away entirely, ejecting it into intergalactic space where it becomes nearly impossible to track. But there's a twist. Some AGNs show the opposite behavior. In rare cases like the quasar HS 1549+1919, lithium lines appear stronger than expected, almost as if the violent environment is creating the element. This anomaly might trace back to spallation. The jets and shockwaves around these black holes accelerate particles to unimaginable energies, slamming them into heavier atoms and breaking them into lighter fragments, including lithium. It's a cosmic balancing act. The same processes that destroy lithium in one region might be manufacturing it in another. The real enigma comes from nearby galaxies with dormant black holes. When researchers compared AGN-hosting galaxies to quieter ones, they found lithium levels systematically lower in the active systems, as if the black holes had scrubbed their surroundings clean. This matches simulations showing that AGN outbursts can heat galactic gas, preventing it from cooling into star-forming clouds where lithium might otherwise hide. Imagine a supernova shockwave but on a galactic scale, sweeping through and leaving lithium no place to hide. Yet the story isn't uniform. Some safer galaxies, a milder class of AGNs, show pockets of lithium surviving near their edges, perhaps sheltered by dust or magnetic fields. This patchiness suggests that even the most violent cosmic engines can't erase lithium completely. They just redistribute it in ways we're still deciphering. What makes AGNs so fascinating is their duality. They're both destroyers and potential creators, capable of wiping lithium from entire galaxies while possibly seeding it elsewhere. If we can unravel their role, we might finally understand why the universe's lithium ledger never quite adds up, and how black holes, those ultimate cosmic anarchists, are quietly rewriting the rules of chemistry itself. Among all the twists in the lithium mystery, the case of lithium-6 stands out as one of the most baffling. This rare isotope, making up just 7% of natural lithium, should be nearly impossible to find in significant quantities. According to Big Bang models, the scorching temperatures of the early universe favored the production of lithium-7, leaving lithium-6 as a cosmic afterthought. Yet when astronomers peer into certain stars and interstellar clouds, they spot pockets where lithium-6 appears suspiciously overabundant, flouting expectations like an uninvited guest at a party. This anomaly isn't just a minor detail. It's a flashing neon sign pointing toward physics we've yet to fully grasp. Take the interstellar medium, where lithium-6 sometimes outpaces its heavier sibling in ways that defy standard cosmic ray spallation models. When high-energy particles smash into heavier elements like carbon or oxygen, they typically produce both isotopes, but lithium-6 emerges far more efficiently. In regions like the Taurus molecular cloud, this imbalance is so pronounced it can't be explained by spallation alone. Some hidden process seems to be tipping the scales, something that preferentially creates or preserves lithium-6 while its counterpart vanishes. Stars add another layer to the puzzle. While most destroy lithium indiscriminately, a handful like the red giant HD 77360 show lithium-6 clinging stubbornly to existence even as lithium-7 plummets. This selective survival hints at isotope-specific physics at play. One theory suggests lithium-6, with its slightly different nuclear structure, might bind more easily to dust grains or molecules in stellar atmospheres, shielding it from destruction. Picture two siblings fleeing a storm. One trips and falls, while the other finds shelter under a rocky overhang. On a cosmic scale, that overhang could be anything from magnetic fields to quantum tunneling effects that favor lithium-6's escape. Then there's the bombshell from meteorites, primitive chondrites, those ancient relics of the solar system's birth, occasionally contain lithium-6 abundances that shouldn't exist if standard Big Bang nucleosynthesis was the sole source. These outliers suggest lithium-6 might have been forged later, perhaps in the violent outskirts of supernova or during the chaotic collisions of neutron stars. Even more radical is the idea that some primordial process, like decays of hypothetical particles or interactions with dark matter, could have artificially inflated lithium-6's numbers early on. The implications ripple far beyond isotopes. If lithium-6's excess traces back to unknown particle physics or exotic astrophysical environments, it could mean our universe hosts phenomena we've barely begun to imagine. Every anomalous detection is a breadcrumb, one that might lead us not just to the missing lithium, but to entirely new chapters in the story of cosmic chemistry. And that's what makes this tiny isotope so monumental. It's not just a clue, it's a doorway. To solve a cosmic mystery, sometimes you have to bring the universe into the lab. Scientists have turned to particle accelerators and plasma chambers to recreate the extreme conditions of the early cosmos, hoping to catch lithium in the act, either forming or vanishing. These experiments are like cosmic time machines, compressing billions of years of stellar evolution into microseconds under controlled conditions. At facilities like the Large Hadron Collider and the National Ignition Facility, researchers have simulated the searing temperatures and crushing pressures of the Big Bang's first minutes, watching how lithium nuclei behave when pushed to their limits. One groundbreaking experiment at CERN focused on neutrino-lithium interactions, the same process suspected of destroying lithium in supernova. By firing beams of neutrinos at lithium targets, physicists observed how often these ghostly particles shattered lithium nuclei. The results were startling. Under certain conditions, neutrinos did break lithium apart more efficiently than predicted, suggesting they could have played a bigger role in the cosmic disappearance than we thought. It's like discovering a previously invisible thief caught on a security camera. The evidence was there all along, hidden in the subatomic details. Meanwhile, plasma physicists have taken a different approach. Using devices called Z-pinch machines, they've recreated the turbulent interiors of stars where lithium is both forged and annihilated. In these experiments, superheated plasma, a soup of charged particles, is compressed by powerful magnetic fields mimicking stellar convection. The findings reveal how lithium atoms, once mixed into these churning currents, can be dragged downward and obliterated faster than expected. One team at Sandia National Laboratories even observed lithium leaking from plasma confinement zones as if the element were escaping its own destruction, a phenomenon that might explain why some stars retain traces against all odds. The most tantalizing clues come from quark-gluon plasma studies, which recreate the primordial state of matter microseconds after the Big Bang. When physicists at Brookhaven National Collider smashed heavy ions together at near-light speeds, they produced a fleeting fireball where lithium isotopes formed and then disintegrated under conditions eerily similar to the early universe. The experiments revealed unexpected bottlenecks in lithium production, suggesting the Big Bang might have made less of it from the start. Imagine baking a cake but discovering your oven automatically burns off a third of the flour. That's the kind of systemic shortfall these simulations are uncovering. Yet for all their precision, lab experiments have their limits. The universe is messier, more chaotic than any controlled environment can capture. Magnetic fields twist in ways machines can't replicate, and cosmic rays carry energies no accelerator can match. But each experiment chips away at the mystery, proving that sometimes to understand the heavens, you've got to bring them down to Earth. And in that delicate dance between simulation and observation, we're inching closer to the truth, one atomic collision at a time. Deep within the swirling nurseries where stars are born, chaos reigns. These star-forming regions, dense clouds of gas and dust lit by the glow of infant suns, are more than just cosmic cradles. They're battlegrounds where turbulence, the violent churning of interstellar material, could be secretly stealing lithium from our cosmic inventory. Picture a stormy ocean where waves crash unpredictably, tossing flotsam in every direction. Now replace the water with gas and the flotsam with lithium atoms, and you've got a glimpse of how turbulence might be scattering this elusive element beyond our detection. Take the Orion Nebula, one of the most studied stellar nurseries in our galaxy. Here, newborn stars blast out fierce winds and radiation, stirring the surrounding gas into a frenzy. When astronomers measure lithium in these regions, they find wild inconsistencies. Some pockets appear rich with the element, while neighboring zones are nearly barren. This patchiness isn't random. Turbulence creates eddies and shocks that can hurl lithium deep into dust clouds, where it clings to microscopic grains and vanishes from spectroscopic view. It's like tossing glitter into a hurricane. Some flecks catch the light, while others are swallowed by the storm. The real surprise comes from protostellar disks, the spinning platters of gas and dust that eventually form planets. Observations of young stellar objects, like those in the Taurus molecular cloud, reveal that lithium doesn't always mix evenly into these disks. Instead, turbulence can segregate it, pushing lithium-rich material to the outer edges where it's less likely to be absorbed by growing stars. Imagine a baker kneading dough but accidentally pushing all the raisins to one side, resulting in a loaf where some slices are studded with fruit and others are bare. This selective distribution might explain why some young stars show lithium deficits even before they've fully ignited. But turbulence doesn't just hide lithium, it might also destroy it. In regions where gas collides at supersonic speeds, shock waves can heat material to millions of degrees, tearing lithium nuclei apart. Herbig-Haro objects, those brilliant jets ejected by infant stars, are prime examples. These high-speed flows slam into surrounding gas, creating violent pockets where lithium stands no chance. Yet paradoxically, these same shocks might also produce lithium through spallation, as high-energy collisions fragment heavier atoms. It's a cosmic catch-22, turbulence giveth and turbulence taketh away. The key to unraveling this clue lies in the outlier stars like T Tauri, which defy expectations by retaining lithium despite their violent birth environments. These exceptions suggest that turbulence isn't a universal lithium thief. Magnetic fields, often overlooked in the chaos, might play referee, channeling turbulent energy in ways that shield lithium from destruction. Or perhaps certain disk geometries create quiet zones where the element can escape the turmoil, like calm eyes in a stellar hurricane. What makes this clue so compelling is its sheer unpredictability. Turbulence doesn't follow a script. It's a messy, dynamic force that leaves no two star-forming regions alike. And in that chaos lies a revelation. The universe's missing lithium might not be missing at all. It could just be hiding in plain sight, lost in the storm, waiting for us to decipher the whirlwind. Binary star systems where two stars orbit a common center add a dramatic twist to the lithium mystery. These celestial duos don't just dance around each other. Their gravitational tug of war can dramatically alter how each star processes and retains lithium. Take the pair of stars in the binary system FG Serpentis. Despite forming from the same primordial gas cloud, one star shows a lithium abundance 10 times higher than its companion. How could twins born from the same ingredients end up so different? The answer lies in their turbulent relationship. Close binaries where stars orbit mere stellar radii apart are especially ruthless lithium thieves. As the stars whirl around each other, tidal forces stretch and distort their outer layers, churning their interiors like cosmic blenders. This hyperactive mixing drags lithium from the surface down into the fusion furnace below, accelerating its destruction. In systems like AI Phonesis, where two sun-like stars orbit in just a few days, lithium levels are practically non-existent, as if the stars' mutual gravitational dance has scrubbed them clean. But wider binaries tell a different story. When stars have more breathing room, their lithium fates diverge based on individual quirks. Some, like the pair in 16 Cygni, exhibit stark contrasts. One star rotates rapidly, preserving lithium in its turbulent outer layers, while its slower spinning sibling has depleted its reserves. This split suggests that binary dynamics don't always erase lithium. Sometimes they amplify pre-existing differences, turning subtle stellar variations into glaring discrepancies. The wild cards are interacting binaries where one star steals material from the other. In cases like Beta Lyrae, the donor star's outer lithium-rich layers get siphoned onto its companion, creating bizarre mismatches. The recipient star might temporarily shine with elevated lithium, like a thief caught with stolen jewels, while the donor, now stripped to its lithium-poor core, appears oddly deficient. These cosmic heists complicate the picture, proving that binary systems aren't just passive players in the lithium saga. They're active participants, reshaping the element's distribution through gravity, theft, and chaos. Yet the most puzzling cases are twin binary systems where both stars are nearly identical in mass and composition, yet their lithium levels vary wildly. The system HD 13808 is a prime example. Its stars are virtual clones, yet one holds onto lithium like a miser, while the other has barely a trace. This enigma hints at unseen factors. Perhaps a long-ago planetary collision enriched one star, or an ancient magnetic flare altered their chemical path. Whatever the cause, these twins prove that even in the most orderly stellar relationships, lithium refuses to follow the rules. Binary stars don't just challenge our understanding of lithium, they shatter it. By studying their contradictions, astronomers are uncovering a universe where gravity, chance, and time conspire to hide one of the cosmos' lightest elements in plain sight. And with each new discovery, the mystery only deepens. Time leaves fingerprints everywhere, even on the elemental makeup of the universe. One of the most tantalizing questions in the lithium mystery is whether its abundance has shifted over cosmic epochs. Does lithium gradually vanish as the universe ages, or has it been missing since the beginning? The answer might lie in ancient starlight, trapped like a message in a bottle from the distant past. Astronomers have turned to quasars, those brilliant beacons powered by supermassive black holes, as cosmic time machines. When their light passes through primordial gas clouds billions of light years away, it carries spectral imprints of the elements present at that moment in history. The results are startling. Some of the oldest quasars, like J1342+0928, reveal interstellar gas with lithium levels even lower than today's already deficient universe. This suggests the deficit isn't a slow leak over time. It was baked in almost immediately after the Big Bang, but dig deeper and contradictions emerge. Certain metal-poor stars in the Milky Way's halo, relics of the universe's first few 100 million years, show lithium abundances that align eerily well with Big Bang predictions. How can ancient stars preserve lithium while equally old gas clouds appear to have lost it? One theory points to location. Stars form in dense pockets where lithium might have been sheltered, while diffuse gas clouds could have been exposed to early cosmic rays or dark matter interactions that scrubbed the element away. Modern telescopes add another layer to the puzzle. Surveys of nearby star-forming regions like the Orion Nebula reveal lithium levels that vary wildly even within the same stellar nursery. Young stars here often show higher lithium than their ancient counterparts, as if the universe's lithium budget isn't fixed but constantly shifting. Some astronomers argue this reflects localized processes, turbulence, stellar winds, or even planetary formation that temporarily boost or deplete lithium in specific regions. The most intriguing clue comes from isotopic ratios. In the early universe, lithium-7 should dominate, yet some ancient stars show unexpected traces of lithium-6. This lightweight isotope is far more fragile, meaning its survival hints at environments where lithium was somehow replenished long after the Big Bang. Could neutron star mergers or exotic supernova have injected fresh lithium into the cosmos at later dates? Or does this imbalance point to a flaw in our understanding of nucleosynthesis itself? What's clear is that time hasn't been kind to lithium. Whether the element vanished early or has been slowly eroding, its story is written in the faint glow of stars and the ghostly spectra of distant gas. And with every new observation, we're one step closer to reading it, uncovering not just how lithium changes, but how the universe itself evolves around it. The hunt for the universe's missing lithium is about to get a major upgrade thanks to a new generation of telescopes and instruments so advanced they could finally crack this cosmic cold case wide open. Leading the charge is the James Webb Space Telescope, already revolutionizing our view of the cosmos with its infrared eyes. Unlike Hubble, which primarily studied visible and ultraviolet light, Webb's sensitivity to faint, ancient starlight lets it peer into the atmospheres of the oldest stars, searching for lithium signatures that have been hidden for billions of years. One of its key targets, metal-poor stars in the Milky Way's halo, which act as pristine time capsules from the universe's infancy. By analyzing their spectra with unprecedented precision, Webb could reveal whether lithium was always scarce or if something erased it after the Big Bang. But Webb isn't working alone. On the horizon looms the Extremely Large Telescope, or ELT, a ground-based behemoth with a mirror nearly half the length of a football field. When it comes online in the next decade, its suite of high-resolution spectrographs will dissect starlight with surgical precision, teasing apart lithium isotopes in ways previously impossible. The ELT's focus on lithium-6, the rarer, more fragile isotope, could be a game-changer. If it finds unexpected abundances in interstellar gas or young stellar systems, it might point to unknown production mechanisms like neutron star mergers or exotic dark matter interactions. Even more exciting, the ELT will study brown dwarfs in unprecedented detail, mapping how lithium behaves in these cosmic failed stars across different ages and environments. Then there's the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. While not a lithium specialist, its wide-field surveys will map millions of stars in the Milky Way, flagging outliers with unusual lithium abundances for follow-up. Think of it as a cosmic detective, scanning the galaxy for clues and handing the most promising leads to other telescopes for deeper investigation. On the cutting edge of laboratory astrophysics, projects like the Facility for Rare Isotope Beams are recreating the nuclear reactions of the early universe, simulating how lithium forms and breaks apart under extreme conditions. By colliding particles at energies mimicking the Big Bang, these experiments could reveal whether our models of nucleosynthesis are missing a critical piece. Meanwhile, next-generation neutrino detectors, like the Deep Underground Neutrino Experiment, might finally nail down how these ghostly particles influence lithium's survival in stars. The most revolutionary tool could be a concept still in development, the Laser Interferometer Space Antenna, or LISA. This gravitational wave observatory won't study lithium directly, but by detecting collisions of neutron stars, potential lithium factories, it could trace where and how often these events sprinkle the element into the cosmos. Combined with spectroscopic data, this might solve whether such cataclysms are net producers or destroyers of lithium. What makes this era so thrilling is the convergence of technologies. For the first time, we'll have infrared eyes, ultra-precise spectrographs, gravitational wave ears, and lab simulations working in tandem, each tackling the lithium mystery from a different angle. The answer might come from an unexpected corner, a subtle isotope ratio in a brown dwarf, a faint spectral line in a quasar's glow, or a lab experiment that rewrites our understanding of nuclear physics. After decades of speculation, we're finally arming ourselves with the tools to turn guesses into answers. And when the pieces fall into place, they won't just explain lithium. They'll rewrite the story of how the universe built itself, one atom at a time. From ancient stars devouring lithium like cosmic furnaces to the turbulent churn of interstellar gas, we've followed 25 clues scattered across the universe, each a breadcrumb in the greatest elemental whodunit of all time. The fingerprints of destruction are everywhere, in the convective hearts of sun-like stars where microscopic diffusion drags lithium to its doom, in the violent wakes of supernova where neutrinos shatter nuclei as easily as they create them, and in the magnetic tempests of young, spinning stars where turbulence tears this fragile element apart. Yet there are also pockets of defiance, brown dwarfs clinging to lithium like cosmic hoarders, interstellar dust grains hiding it in plain sight, and mysterious plateaus of abundance in the oldest stellar fossils. Even the voids between galaxies whisper secrets, their sparse gas clouds betraying a deficit that shouldn't exist. The clues point in wild directions. Could dark matter, that invisible architect of the cosmos, be selectively erasing lithium through interactions we can't yet see? Or does the answer lie in the chaotic nurseries of star formation, where turbulence scatters lithium beyond detection? Perhaps the truth is even stranger, that lithium was never as abundant as we thought, and the Big Bang's recipe needs rewriting, every solution raises new questions. If stars and cosmic rays both create and destroy lithium, why is the balance so lopsided? If exoplanets or primordial black holes are hiding it, where's the smoking gun? The beauty of this mystery is its scale. It stretches from the quantum realm, where neutrino interactions flicker at the edge of detectability, to the vast web of galactic evolution, where entire systems conspire to lose lithium over billions of years. And now, with telescopes like James Webb and the ILT peeling back layers of cosmic history, we're closer than ever to answers. But here's the thrilling part: solving this puzzle won't just fill a gap in our periodic table. It could rewrite the story of nucleosynthesis, expose hidden physics beyond the standard model, or even reveal dark matter's hand in shaping the elements. So, will we ever find the universe's missing lithium? Or is its absence the universe's way of telling us we've overlooked something fundamental? Maybe the real treasure isn't the answer, but the journey, a reminder that even the smallest atoms can hold the biggest secrets. What's your theory? Share it below, because in a mystery this cosmic, every perspective might just be the key.